Hello everyone, I'm Eun-Kyu Park from Seoul National University. Today on behalf of my amazing collaborators, Minyoung and Ganyi, I will introduce our CVPR 2025 paper, HalLoc, a benchmark and method for token-level hallucination localization in vision language models. This work is about understanding not just whether a model hallucinates, but exactly what, where, and why. We begin this research with the fact that vision language models hallucinate frequently. Even when given real images, they often mention objects or attributes that aren't there. Existing hallucination detectors rely on powerful models like GPT-4 or provide only binary judgments and/or are too slow for practical use. We aim to go further, to localize hallucinations at the token level in a scalable and interpretable way. Our goal is to build a dataset and model that detect hallucinations in a fine-grained, fast, and scalable manner. Our research today and our presentation today is guided by three questions. First, can we build a scalable and controllable hallucination labeling dataset? Second, why aren't token log probabilities sufficient to detect hallucinations? And third, can hallucination localization help models generate better grounded outputs? To this end, we present HalLoc, the first token-level hallucination localization dataset. It contains over 155,000 samples across three core tasks: visual question answering, instruction following, and image captioning. Each example is annotated at the token level with one or more hallucination types: object, attribute, relationship, or scene. The dataset is model agnostic and can be used to evaluate or train most vision language models. So, how did we build HalLoc? We propose a scalable two-step pipeline. First, we hallucinated answers for image-based questions in existing VQA datasets that cover different and diverse types of failed answers. Then, we inject these hallucinated answers into real VQA instruction and captioning examples pertaining to the same images. We use the GPT-4 to ensure contextual coherence and fluency and semantic correctness. This pipeline gives us a scalable, type-specific hallucination annotations that are verified and token-aligned. We define hallucinations at the token level with four distinct categories. Object, referring to non-existing items like a phantom shower. Attribute, referring to incorrect properties, like saying a shelf is glass when it's wood. Relationship, referring to wrong spatial or action-based links, like a mirror above a sink when there is none. And lastly, scene, which refers to errors in environment, such as misidentifying a kitchen as a bedroom. This granularity allows us to pinpoint exactly what is wrong and why. To simulate different failure modes of VLMs, we inject hallucinations by manipulating three sources. First, we simulate hallucinations from the vision encoder, where the model misinterprets the visual context alone. Second, we simulate frequent mismatches between vision and language embeddings in the connection module. And third, we simulate cases where a model hallucinates due to textual context alone. These three sources aren't just random. They reflect real-world failure modes in most vision language pipelines. By controlling them when we craft hallucination, HalLoc achieves modular robustness in VLM generations and failure attributions. Using HalLoc, we train HalLocalizer, a lightweight hallucination detector which encodes the image-text pair and for each token predicts a hallucination score for each of the four types that we just defined. The model is efficient enough to run during generation to predict hallucination probability for each token. Now, the fact that HalLocalizer outputs hallucination probabilities naturally raises a question. Why not just use existing token-level log props? Our answer is they're not enough. While log props may reflect uncertainty, they fail to identify specific hallucinations in subtle cases like attribute and relationship failures. Our model, on the other hand, assigns high scores to hallucinated tokens in the correct type, while log props remain mostly flat. Now, as shown in this table, HalLocalizer achieves much higher F1 scores across all types and dramatically lower ACE scores, meaning the scores are also better calibrated. This highlights the importance of explicit type-aware supervision rather than relying on shallow uncertainty signals. We also tried using hallucination scores to revise model outputs to answer our third question: do token-level localization actually help? By flagging hallucinated token spans, HalLocalizer helps models edit and revise the correct spans and generation at fine granularity, making responses more grounded with higher CIDR scores. A thing to note is that it gets closer to revisions guided by ground truth misidentification just by localizing hallucinated tokens. To summarize, we present HalLoc, a token-level hallucination localization dataset with over 155K examples. We also introduce HalLocalizer, a simple and efficient model that outperforms log props and enables grounded revision. Both tools help us move beyond black box judgment towards an interpretable, type-aware hallucination understanding. Thank you so much for listening, and feel free to reach out to us via email or visit our GitHub to learn more. Thank you.